right, I guess let's start. Okay, so we're going to continue on policy gradient. So in addition to the formulation that we saw last week, we're going to talk about another two formulation, which are the more common versions that people use actually in practice, right? But first, let's do a recap. So we started talking about, parameterized policy, and then, compute the gradient with respect to the parameters of the policy, right? So that we can take, gradient ascent to optimize the parameters of our policy. Right, so like two of the most common parameterization people use is the softmax linear policy, which is the one that you will try it out in your homework. And the second one is this neural policy, right? So all it's doing is that it's introducing a parameter, theta, and then use theta and the feature vector phi together to approximate some function, right, for a state action pair. And then you add softmax on it. So if there's two actions, so simply think about this as a logistic regression parameter, right? It's linear logistic regression. So in other words, if you only have two actions, positive 1 or negative 1, right? So we can just represent this as the usual logistic regression parameterization. So the formulation that I wrote is basically, the one corresponding to multi-class, right? So this is like logistic regression for multi-class classification, right? And of course, you can replace the linear part inside this softmax by a neural network, right? So this will be more expressive. So you should convince yourself, this parameterization pretty much can parameterize every possible policy, right? So if f theta's range is from, for instance, negative infinite to positive infinite, then pretty much this function can approximate any policy, right? A uniform policy or a policy that puts all the probability mass on a particular action, right? Because you have this exponential on this value. Right. And I was saying this is essentially just a multi-class, a multi-class classifier that parameterized by neural network, for instance. Right. So you have some neural network feed-forward layers. Your input is S. Your output is a distribution over your actions. Right? Imagine you're doing 3-class classification. This is the neural network you're going to do, right? So you add multiple layers, and then the last layer you add the softmax. So you output a distribution over actions, over your labels. Okay, so yeah, so in high level, think about pi theta as a classifier, right? So this is a multi-class classifier, which has its own parameters to be optimized. All right, and then we talked about the most classic algorithm, reinforce, which is an algorithm that computes the policy gradient. Right, the way we do this is we start from a trajectory. So here I'm doing finite horizon. So in the class we did the infinite horizon derivation, right? So here I'm going to show you the finite horizon one, but the derivation is basically the same, the importance weighting thing, okay? So this is a finite horizon trajectory, and I can write out the likelihood of a trajectory by just using the Markovian property, right? The likelihood of sample S0, the likelihood of sample the first action conditioned on the first state, and likelihood of transit to the next state S1, so on and so forth, right? I can just write out this likelihood as a product of these many terms. Okay, great. And what is our objective function, right? Our objective function is nothing but just the expected value, right? Taking the expectation with respect to the trajectory distribution, right? And inside the expectation, it's just the total value of this trajectory, right? The sum of the rewards across this trajectory. So that is literally our definition of total reward, right? Okay, so this function is a function of theta, right? You give me a theta, I give you a value for that. Right? So that means that we can compute the gradient with respect to theta. And the way we do this is that we use importance weight. Right? So this is the final formulation that we get. But to recap, let's just go through that process again. Right? So I'm trying to compute this guy, right? And maybe at theta equal to theta 0, right? Theta 0 is the point that we're trying to compute gradient, right? So this is the point that we're going to evaluate our gradient. So by definition, this is right. I'm just writing out the definition of our objective function j. And now let's do this importance weighting trick. I'm using the current parameterized trajectory distribution as my sampling distribution, right? Right. So I just, multiply rho theta 0 and then immediately divide. Okay, so now great, I can push the expectation, I can push the gradient inside the expectation, right? Because the expectation has nothing to do with my parameter theta anymore. Zero gradient of theta tau. Right, I just push the gradient inside the expectation, and notice that among the three terms, only the first term, only the term on the numerator depends on theta, right? So I just take gradient with respect to that. And now using the chain rule for log, right? So this guy is just equals to gradient theta log of rho theta tau measured as theta equal to theta 0, right? Just by chain rule. Okay, so great. So this now gives us this. Right, so this is our formulation of the policy gradient. Right, so this is essentially saying that you should adjust the parameters such that your trajectory likelihood actually put high probability on trajectory that has high reward, total reward. Right, so that's why we are weighting this gradient. We are weighting this gradient by using the trajectory reward. Right, so you should actually prioritize on trajectory that has high reward, and prioritize less on trajectories that has less reward, right? And you have to do it in proportional to the total reward. So that's this multiplication is talking about. Right, so this totally makes sense. But the issue, we talked about is that we cannot compute the likelihood, the trajectory likelihood, right? Because this is unknown and this is unknown. Right? We cannot, implement the likelihood computation, for instance, in our program, right? But what we realize is that when we compute log of the trajectory likelihood, right? So this is gradient of likelihood of mu as 0 plus log of pi theta a0 as 0 plus log of p as 1 as 0 a0, so on and so forth, right? And now you push the gradient inside this summation, and we realize that this term will go away because this term has nothing to do with theta. This term will go away because this term has nothing to do with theta, right? So these are the things that are defined immediately when we define the MDP, right? This has nothing to do with the learning. So this is just given, right, when we are given the problem. So that eventually leads to this expression. Right, so this we can compute because policy pi theta is the parameterization we choose, right? Like we pick this parameterization and we implement it and we take gradient with respect to that. Right, so we can do that. That is basically the derivation of reinforce. right? So in high level, we're trying to adjust.
I have a question.
Yes.
Why is it the gradient of theta with regards to ln pi theta 0? Then wouldn't that also go to 0 because theta 0 is just a value, not a variable?
Sorry,
And
see it again.
so in the summation, you have gradient of theta ln pi theta 0, but pi theta 0 is just a value.
Oh, sorry. Yeah. So think about this. Okay, so think about this as so this is it's a short notation. So think about this as more formally, this should be this, and evaluate at theta equals to theta 0.
Okay.
Right. Yeah. So in high level, we are trying to adjust the trajectory likelihood, right? So that you gradually put more and more probability mass on these promising trajectories, meaning the trajectory that has a high reward. But we cannot directly do it, right, through the trajectory distribution because we cannot control it. The way that we do it is indirect in the sense that we control our policy. Right, as you can see from the previous derivation, this has nothing to do with either you're doing infinite horizon setting or finite horizon setting, right? The same derivation, the same importance weighting, the same fact that when you take a gradient of the log of the trajectory likelihood, a bunch of terms become 0, right? The terms that does not depend on the policy will just become 0. And now we get to the ground truth formulation for policy gradient. And how can we get an unbiased estimate from it, right? So that we can do stochastic gradient update. So we just need to replace the expectation by a sample or multiple independent samples, right? So just draw a trajectory from this distribution. And the way you draw this trajectory is execute policy pi theta 0 from S0 from the initial distribution, right? Just starting from the first time step, draw a trajectory, right? So that trajectory is a sample from this distribution, trajectory distribution, right? And then just replace this expectation by this sample using this sample, right? So this is an unbiased estimate, and adding the expectation, this will equal to the gradient, the true gradient.
Professor, I have a question.
Yes.
This only works in the case that you have a limited number of steps, right? Like 8 steps or something like that.
Yeah.
What happens when you go, like, I remember we were discussing before in the infinite horizon as well. Like,
yeah, good question. Yeah, good question. So infinite horizon, yeah. So technically, you have to draw infinite many steps. But remember, every step is discounted by gamma to the power of h, right? So imagine gamma equal to 0.9, and do you really need to care about steps after 1,000 steps? Gamma to the power of 1,000 is pretty much 0, right? When gamma is to 0.9, for instance, right? So you can properly discount it. Yes, you will get a biased estimate of the gradient, but the bias is tiny. The bias is like exponentially small.
The same method, like we use the rollout method before to get an unbiased estimate of the Q,
right? You will see in this lecture.
Okay.
Yeah.
Also, I was wondering in practice, like how you actually take the gradient of a policy. Maybe we'll go over that this lecture, but I was curious.
We don't, but you will. So there are two ways. First way is you do it manually, right? So imagine this pi theta. AS is proportional to exp of theta transpose phi SA. So add the log on it, take a gradient. You can do it by hand, right?
Okay, yeah.
Another way is this neural thing.
Oh, that's what
just implement it using TensorFlow, for instance, right? And then ask TensorFlow to do dot backprop. Then you get a gradient.
Got it. Thank you. Oh, also, I was wondering if today's slides are going to be posted.
Shoot. Okay.
See
Sorry about that. Yeah, I okay. Let me just post it right after the class. Sorry about that. Yeah, I forgot.
And when do you want me to help you post it now?
Oh, yeah. You actually have access to, right? Okay, cool. Great. Yeah.
Thank you.
Right. So in the homework, you will try out this way, and you will compute the gradient, the analytical formulation of the gradient by hand, right? And then you will do the policy gradient. But the nice thing of this policy gradient method is that you really like the parameterization of the policy could really be black box, right? Especially today, we have this backpropagation tools that people developed in TensorFlow or PyTorch, right? You can really make it super complicated as long as backprop can still do it, right? This neural network could have 1,000 layers. It doesn't really matter. You just call like TensorFlow.backprop, right? It computes the gradient for you. Right. So, but this
super expensive. So let's say H is pretty large. If you have a neural network to compute the probability, let's say even if it's 100 layer or 200 layer neural network, wouldn't the complexity increase with H like significantly each time? Because you're computing like every time you're going forward prop, back prop again for every single pi theta of AH given SH.
Yeah. So that computation you have to pay, right? You have to suffer that computation. Yeah. But the way you can do it, you just generate data, right? You generate a trajectory, and then you just need to do backprop in parallel. Like you don't have to wait, right? Like generate a trajectory first, let TensorFlow take the whole data set and then do backprop on every data point in parallel, right? It's like you can just naively parallelize it, right? Okay, but this approach has an issue. I mean, this is one of the reasons that people do not use it directly in practice, right? But the problem is that this formulation will have high variance. So this is a random quantity, right? Because this depends on a trajectory sampled from this distribution. So this is a random quantity, and we can reason about the variance of this random quantity, right? So I'm not going to go to the details of this, but the variance could be as large as h to the power 3, h cubed, right? So one of the reasons is this term is roughly around h, right? Because this is a summation over the entire trajectory, right? And when we do expectation of g square, because we care about variance, right, which is the second moment. So this is like roughly equal to summation h equal to 0, h minus 1 of h square, right, because of this guy. So when I add expectation, when I add g tau square, this is roughly h square, right? So that's why I roughly get a h cubic variance. Right, so when your h is big, your unbiased estimate, it is unbiased, but the variance is huge, right? And when you do stochastic gradient descent or gradient ascent, the huge variance is going to affect your convergence rate. Right? Yeah. So this is, the most classical formulation. People invented it in 1992, and later on, people developed some improvements on this version, which we will cover today, which are actually the versions that people implement in practice. Right. So that leads to today's question. So can we develop some improvements to reduce the variance in policy gradient? Right. And then the outline for today is that we first are going to look at a policy gradient version that uses the Q function. Right. So let me write this Q pi. And then the second topic that we want to cover today is that we can further reduce the variance by using the advantage function. Right. So this is a pi. Just remind you that advantage is the difference between Q and V, right? The advantage of, deviate from pi for one step. And then, the last bullet point, we're just going to put everything together and show a pseudocode framework. Right? So any questions so far before we jump into, today's materials? Okay, great. Yeah, so just some quick recap on the notations. So we're just gonna focus on infinite horizon setting, but whatever we're gonna cover today, they just trivially applies to finite horizon, right? So convince yourself, the derivation that we're gonna do today, they naturally applies to finite horizon setting. All right, so let's record the definition of value function b pi. So that is essentially saying that if I start from S and execute a pi all the way to the end, what's the expected total reward with proper discounting, right? And the objective function can literally just written as the expectation with respect to the initial state, right? And then inside the expectation, it's just the value of the policy at that particular state S0. Right, so this is one of the problem in homework 0. Okay, and again, the usual state action definition, distribution definition, right? The infinite mixture of infinite distributions, and then the advantage definition, right? So these are the definitions that we're going to use, right? Hopefully at this stage, you're pretty confident about these notations. Okay, so let's just jump into deriving a policy gradient formulation using the Q value. Right, so if you record the reinforce, one of the term of the reinforce looks like this. Right, so there's a summation over H, but one of the term that looks like this, right? So this looks a bit weird because I'm at time step H, but when I multiply this scalar, I'm still looking at the entire trajectory as reward, right? So that doesn't really make that much sense because considering this Markovian property, like if I'm at a state SH, if I change my action AH, that only going to affect the future, right? So this is not really going to affect the history. Like conditional SH, the history is the history. Like now you're making an update on action, that should only affect your future, right? Just from this causality perspective, like this thing is weird. Maybe we should only concern about the future, right? So instead of our tau, maybe we should just concern from tau equals to h to infinite and gamma to the tau of r as tau a tau. Right. So instead of worrying about the entire trajectory, the history is the history. Maybe we should just weight it based on the future, right? Because after all, if we update this action at this time step, it's only going to affect the future, right? So this is what are we going to do here? And you will see, actually, we can just write this using the Q function. Right, so that totally matches our intuition because
this work because isn't the Q function an expectation over all the
yeah it is but it is, but think about in a conceptual level, right? Like I'm updating my action A at this time step. This should really affect the future, right? Not the history. Like conditional SH, the history is a history. Like the history is independent of the future. Conditional SH.
No, so conceptually that makes sense, but mathematically, like it's an expectation of both the policy change and
So let's add expectation on both sides.
Oh, okay.
Right. So then it's fine. Yeah, we will see. When we get to this derivation, right? Okay, so this formulation is the formulation that we are aiming for in this slides. Right, so that also nice because this significantly reduced the value of this tau, r tau, right? Instead of at every time step, no matter which time step I am, instead of considering the entire total trajectory's reward, I'm only going to worry about the reward starting from the current time step. All right, so let's just do it. Okay, so let's start from the definition, right? So I want to compute a gradient with respect to my objective function. I'm just writing out my objective function using the value function here in the first time step. All right. And let's just do one more step. This expectation is independent of my parameter, right? Because mu is the initial state that is given. It has nothing to do with the parameterization. So let me just push the gradient formulation inside the expectation, right? So this is the expectation this is the formulation that I get. I'm writing out one more step by taking action A0 from this policy, right? So here I'm using this notation in short of this notation. Right, so basically, I'm just saying that the action is sampled from this parameterized policy, conditional on a particular state. Right, so nothing magic here. I'm just pushing the gradient inside the expectation and write out one more step, right? By explicitly writing out the expectation with respect to the action, the first action A0. Okay, so now we want to push the gradient again through this expression, right? But this expression is a little bit complicated because we have two terms. The expectation depends on theta, and the term inside the expectation depends on theta too, right? So there's a theta and there's a theta here, right? So now we get into a situation where we needed to apply this product rule for gradient, right? So if I have f and g and we'll take the gradient of that, this is like the gradient of f times g plus f times g, the gradient, right? So we are exactly in this situation because we have two places where we have the parameter. So let's just apply the product rule, all right? And if you apply the product rule, this is what you get. Right? So let's just go slow. Let me just derive this step. Right? So what is this guy? Theta. I'm just writing summation. I'm just writing the expectation using summation. Okay. Right. Apply this product rule. This is summation over A of applying gradient on the first term while I leave the second term unchanged, right? Plus summation of A, where we leave the first term unchanged and apply the gradient on the second term. Right, so this is literally a product rule, right? I'm doing this like fg prime equals to f prime times g plus f times g prime. That's literally the product rule that I'm doing. Okay. Product rule. Okay, so now I'm using the importance weighting trick again. Right. So this new line is almost the same as the previous line, except here I'm applying this trick. Right? I just multiply this pi theta, and then I immediately divide it. So these two should go away. You should convince us this new expression is exactly the same as the previous line. Right? I'm just multiply something and I immediately divide. And I did one more step here. Right? So I push this gradient through this Q function. So let me write out this step. Gradient theta, Q pi theta, S0, A0. So what is this guy, right? Let's apply a Bellman equation on it. Gradient theta, R S0, A0 plus gamma, expectation of S prime, S1, right? This looks pretty nice because the reward has nothing to do with my theta, right? So the gradient of the reward is 0. And again, this is nice because the expectation is with respect to the transition, which has nothing to do with my parameter, right? And that means I can push the gradient inside the expectation. Right? So all I did is just a Bellman equation and then, apply gradient on each term. Right? The nice thing is that reward is independent of the parameter and the transition is independent of the parameter. Okay, so now we arrive at this formulation. Right? And the reason that I write this term, this more complicated term, is that I want to apply the log likelihood trick. Right? So this term, I can just write it as expectation of A0 from pi theta A0 S0 of gradient theta log of pi theta A0 S0. Right? Again, by chain rule. All right, so let's just do that. So now we get this expression, right? So here in this step, I applied the chain rule for log. Right, and from this step to this term, I just rewrite everything in terms of the distribution, the state distribution at the first time step, right? Because how did I, So how did I get S1? So S1 is based on S0 that sampled from the initial state and pi 0 sampled from our policy pi theta, right? So that means S1 is indeed coming from this distribution, right? The distribution at time step 1 that is parameterized by policy pi theta. Okay, so this is great because here we can already repeat the same process, right? In other words, we can just do recursion, right? Because we start from this step, right? We started from taking the gradient with respect to the value function at first time step. Now we get it to a place where we can take gradient with respect to the value function at the next time step, right? So we exactly get back to the original situation, except that we moved one step forward in time. Right? So if you just repeat the same process one more time step, we get this second term, right? And now we moved one more time step forward till we get to time step 2. Right? So this step is repeat the same process on this term. Right? And then now you can repeat the same process on this term, so that you can move on to time step h equal to 3, and so on and so forth, all the way to the end, right? And the nice thing is that every term has a discount factor here, gamma. Right, so let's just imagine that we repeat this process for infinite many steps. We correctly counting the power on the gamma. Then this is the expression we get. Right, a summation over infinite many steps, but each step is weighted properly by the discount factor to the power h times the log likelihood of the policy, the gradient of the log likelihood of the policy, scaled by its corresponding Q value, right? So this was our goal. And now use the state action distribution, the average state action distribution, we can write it in even more succinct way, right? So basically, we're just looking at the state action generated from our current policy's distribution, right? And we take the gradient of the log likelihood of the current SA pair, and we scale it by the corresponding Q value. All right, so that's the expression that we get. So what we did, right? Use product rule plus importance weighting plus recursion for infinite many steps, we arrive at these two formulations. Right? So here we're just using the definition d pi theta mu. All right, so now let's think about why this expression makes sense, right? What does it do? Like what is it doing, right? Yeah, so for finite horizon, you can do the same process and you will get similar expression, right? Except that now your Q value is dependent on the time step. All right, so literally this is saying that I should adjust my parameter theta such that I will actually make sure my new policy increases the likelihood of picking an action whose Q value is large. Right? And I should decrease the likelihood of picking an action whose Q value is small. Right? So that totally makes sense, from the policy improvement perspective, right? Remember when we do policy iteration, what we are saying is that we can always be greedy with respect to the current policy, right? And we guarantee that we will make an improvement. So policy gradient is essentially saying that let's just do this step slowly. Let's just, gradually increase our likelihood on an action whose Q value is big and, proportionally downgrade the probability, the likelihood of an action whose Q value is small. Right, so that's literally what policy gradient is doing. So it's reasoning, the likelihood of the action based on the Q value.
So I'm a little confused. Why is that? So in this case, since we're taking the gradient, isn't the whole point to make the gradient closer to 0 to maximize, given that we're looking for a local optimum? So
yeah.
So the question is how is that intuitive? I get that you have to do that conceptually, but why does this equation show that? Because this is the gradient, right? So you want this to be as close to 0 as possible. So
yeah. So you want to make this gradient, the norm of this gradient, to be 0. Correct.
So then how do you, from this equation alone, how do you know that you're supposed to be putting more weight on values with higher Q and less weight with values in a lower Q?
Yeah, so good question. So imagine that we are at an optimal policy, right? So we had pi star, right? So what's pi star? Sorry, so pi star is a deterministic policy, right? Right, so in other words, pi star AS equals to 1, if A equals to pi star S, 0 otherwise. Right, so pi star is the deterministic policy, so I'm just representing the deterministic policy by this delta distribution, right?
Yep.
So let's just plug it in, right? Okay, so should convince ourselves this guy is always 0. Because your trajectory, your state action distribution is sampled from pi star.
Yep.
Right? So this likelihood is either 1 or 0. But on the state that on the action you sampled from pi star, it's always 1. It's a constant, right?
Yep.
So in this case, this is 0. The whole expression is 0. Right? So this checks out at the optimal solution, at the optimal solution, right?
But what is ln of 0?
What is what?
ln of 0, the log of 0. If A is
it's
not
log of 1. It's log of 1. You're never gonna pick an action whose likelihood is 0 because this is sampled from your optimal policy.
Oh, so you're just good. Oh, I see what
SA
you mean.
is from d pi star.
Yeah.
So you're never going to pick an action whose probability is 0, right? Imagine how you execute the optimal policy, right? You're always going to pick the action that determines by the deterministic optimal policy, right?
Yeah.
So your policy likelihood is always 1 on the action you selected.
So wait, I have a question then. Wouldn't any deterministic policy also give you a gradient of 0?
Yeah. So this one does not work for deterministic policy.
No, so as in like, even if you don't, so isn't the aim of this like literally if it reaches a deterministic policy, it's reached a local optimum, right? So how you can't really say that deterministic policy
So
is going to be
you should. So for this algorithm to work, you should never start from a deterministic policy.
Yeah, no, so that I get, but like if it like somewhere halfway through it reaches to a deterministic policy.
Yes,
right?
you're done. Yeah.
So, but that doesn't even have to be close to the optimum, right? How do you guarantee that this?
No. So you cannot guarantee global optimality for this solution.
No, not even global
descent.
optimality, but like, how do you know that this is actually giving you a value that is like better than the previous step? Like,
just by that, if you want to argue that like why this makes an improvement, this is just a gradient descent improvement.
Oh, because it's just gradients.
I'm just doing gradient descent, right? Gradient descent with infinitesimal small step that improves the gradient, that improves the objective value, right?
Yeah.
Like this is literally the gradient. I'm not like doing anything, magic, right? This is literally the gradient of the objective function.
Yeah, that makes sense. So it's basically a really non-convex thing where if you hit like a local optimum, it's over.
Yeah. So you're right. There's a caveat, right? So we should never start from a policy that is deterministic. Right. So this is like, when you do backpropagation for neural nets, right? You should never start with initialization to be 0.
Yeah.
Because that's not going to work, right? And during the training time, at some point, your weights just become 0, then you also stop there as well, right?
Yeah.
Yeah.
Okay.
Right. Any other questions? Okay, cool. Yeah. So now let's look at another expression that uses the advantage function rather than the Q function. Right. So again, using the advantage function kind of makes sense in the sense that, we want to sort of adjust our policy such that we give action that has large advantage, high probability, right? We want to upgrade the probability of an action that induces large advantage against the current policy, and we want to downgrade the probability of an action whose advantage against the current policy is small, right? So if an action has large advantage, maybe we should play it more often in the future. So that's essentially what's seen, right? And hopefully that improve the policy, or improve the current policy. Yes. So recall the derivation that we had for the Q version, right? So this intuitively is saying that we should slowly adjust our policy such that pi theta gradually puts more weight on the action that has large Q value. Right. So in other words, you want to be a little bit greedy with respect to the current policy, but you don't want to be exact greedy, right? Because we learned from the previous lecture that be too greedy, like the approximate policy iteration is doing, this is not guaranteed to be converged, right? So here we are saying, let's just be a little bit greedy. Let's just move towards that greedy action a little bit by increase the probability a little bit, right? But maybe we can do the same thing for advantage, right? Because after all, from the policy iteration algorithm, we know that being greedy with respect to the advantage function always guarantees improvement, right? Subject to the fact that we know advantage everywhere, right? So in policy iteration, what we said is that if I set new policy to be the argmax over A of A pi theta SA, then I know that pi theta will be bigger than, at least as good as pi theta. Right? So that's what we proved in the policy iteration. So that means actually, selecting an action that has large advantage is actually good. Right? So that actually motivates, why we want to derive a policy gradient formulation for the advantage function, right? We want to gradually update the parameter of our policy so that this policy in the next round will select an action that has high advantage against the current policy. All right, so that's the formulation that we will have. So what I did here is exactly replacing the Q function by advantage function. So this is a fact, right? So my policy gradient will exactly equal to this guy. And to show that, we will prove a more general version. Well, let's write this function, which is called baseline. So B is a function that maps from state to real. But one of the important thing is that this function is action independent, right? So this is just state dependent, and this is action independent. And what we will prove is a more general result in the sense that the policy gradient actually can be written as this formulation, where I can I can replace the Q by the difference between Q and the baseline. All right, so why this leads to this formulation? Let's just set Bs equals to V pi theta S. Right, so in other words, if we prove this policy gradient formulation holds for any baseline that is action independent, we can just replace this baseline by the current value function, which we know is action independent. Right? And then we can just plug it in and we get an advantage function. All right, so how to prove this policy gradient actually equal to this mu formulation, right? So all we need to do is just to convince ourselves that this term is 0. Right, because we know that the policy gradient can be written as using the Q value right? So recall this is the Q value version, the Q function version of the policy gradient. And what we are saying is that we can just minus a baseline function B at the state S, and then the gradient is not going to change, right? So all we needed to prove is this term is 0, right? And then we prove that these two formulations are equivalent, right? So that's not harder to do. So let's just prove this term is equal to 0. Right? In other words, just take the expectation with respect to the action. So this holds for all S. And look at the log likelihood, the gradient of the log likelihood of the policy, and then multiply this baseline. So we will show that this term is 0, regardless of what B you use. All right, so the way we do it is let's undo the importance weighting trick. Right? Let's undo let's apply chain rule and let's undo the importance weighting trick. Right, so here I'm just writing out, so apply the chain rule. Right, so this gives us log of theta pi theta ALS divided by pi theta AS. Right, so I'm just applying the chain rule on this gradient of the log likelihood of the policy. Okay, so this is nice because these two terms cancel now, right? So what I get is this new expression, because again, these two canceled. And I put this function B in front of the summation because this is action independent. Right, and I can also pull the gradient formulation outside of the summation. So now I get to this formulation, right? Okay, so this is nice because this is a valid distribution. In other words, summation over A is equal to 1, right? Now the gradient of 1 is equal to 0. So which means this whole term is equal to 0. right? So this is how we convince ourselves that this is equal to 0, right? Adding a baseline that is actually independent is not going to affect the gradient. Okay, so let's just do a quick summary. So by using a baseline, it's often read as B, taking the value at state S. So it's important this is action independent. This is a function that only depends on state, does not take action as an input. Okay, so we can design any such kind of function. It could even be a constant, right? And we can just immediately minus it in this formulation, and it does not change the expression of the policy gradient, right? Because we proved that A from pi theta S log pi theta AS times B S equal to 0. That's what we just proved, right? So that means that just plugging in a baseline is not really going to affect the expression of the policy gradient. And the most common thing we do in practice is that set this baseline to be the current policy's value function, right? So if I set this to be theta S, again, the reason that I can do this because my value function is a function dependent on S, right? It does not take an action as input, right? So that gives me the advantage version of this policy gradient. Right? Again, this thing is that I want to adjust the parameters of my policy such that the likelihood of picking an action that has large advantage should be properly increased, right? I should downgrade the likelihood of picking an action whose advantage is negative, for instance. Right. So we can actually show that baseline indeed can help reduce the variance of this estimator, right? But we're not going to do the formal proof of this variance reduction here. So basically, the intuition behind this is that when we do the finite sample version of the policy gradient, right, by minusing the bonus, by minus the baseline, so we reduce sort of the value of this expression. Right? And that helps the variance because you have a random variable whose range is actually getting smaller, right? By minus the baseline. Especially, your baseline is the value function, right? So Q pi theta SA minus V pi theta S. Your hope is that Q pi theta SA is not too different from V pi theta S, right? Because after all, they only disagree at the first time step, and later on they follow the same policy all the way to the end, right? So you only deviated a little bit at the first time step, and afterwards, you two are using the same strategy. So hopefully the difference between these two is not so big, right? So that could dramatically reduce down the range of a random variable, which helps reduce down the variance, right? Because the variance of a random variable is the expectation of the square of that random variable, right?
So just to clarify, if you use like a different baseline that wasn't v sub pi theta, then that doesn't necessarily lead to variance reduction, right? Because intuitively, I feel like if you just made the baseline like 5 or like some just constant number, then the variance shouldn't change, right?
The variance in the worst case will not change, yes.
Right, okay.
So the worst case, even if you use pi theta, it will not change, right? So imagine the setting where you actually take a action and then you fall off the cliff, for instance, meaning that the difference between Q pi SA and V pi S is equal to H or equal to the horizon. That could be possible, right? Maybe, you make a mistake at the first time step, you fall off the cliff, and regardless of what you do, you're always gonna receive reward 0, right? But we hope that in practice this is not gonna this does not happen, right? In the sense, your system might be actually Lipschitz continuous, in the sense that you're taking an A and the difference is not that big, right? So imagine the case where this is a L Lipschitz function with respect to A. So then, Q pi theta SA minus V pi theta S, they are literally just bounded by the Lipschitz constant times, the difference between A and pi theta S roughly, right? So hopefully this is a small number. Hopefully our system is well behaved in the sense that you change the action a little bit here, the value is not going to change, right? But in the worst case, your Q function could be actually ill behaved in the sense that you just take a run action, you're immediately going to be penalized, right? So in the worst case, it's also not going to help.
I see.
Yeah. And a fun fact is that you can actually literally compute the best baseline that minimizes the variance. You can actually analytically compute that, right? And if you do that, you will see that the best baseline is actually not equal to V pi theta. It's a very complicated expression.
This might be a stupid question, but what's the difference between this and just using a smaller step size with your gradient ascent or descent algorithm?
Yeah, so step size, so here we are still doing the same, like we're just deriving the gradient expression for now, right? And we are reasoning about, if we get an unbiased estimate of the gradient, what's the variance of that unbiased estimate, right? The gradient step size is, in some sense, it's different from, it's different from what we are doing here, right? So that is another hyperparameter you needed to tune. So here, I'm just saying that we cannot get the exact expression of the gradient, right? Because of these expectations, we can only use samples. But let's make sure, we get to a formulation where the sampled version has the smallest variance, right? And on top of that, you can tune your learning rate, right? But if I give you an unbiased estimate of the gradient, which has huge variance, that's pretty bad, right? No matter how you tune the gradient, because the variance is large. Like you are guessing the gradient. Yes, your guess is unbiased, but the variance is huge, right? So that's no good, right? Because we want to actually have an unbiased estimate whose variance is small.
Professor, so when you have Lipschitz continuity, can you put the same bounds on the convergence of gradient descent as you can for any other problem with Lipschitz where Lipschitz continuity holds? Like, this only works for when you're doing Q pi 0 of S comma A minus V pi 0 of S, but does that apply overall to the problem itself? Like, can you say that the convergence is the F0 minus F star divided by 2t plus sigma squared A squared sigma squared L by 2 or something like that, right?
I mean the convergence rate for gradient descent.
Yeah, can you use that over here, for stochastic gradient descent?
So that's a good question. So what we showed is that if your function is smooth, then you can guarantee this. Right? Okay. Lipschitz continuous. So you have to be a little bit careful because Lipschitz continuous. First of all, it doesn't really mean that the function is differentiable.
Oh yeah, that is also true. Yeah.
Yeah, I don't recall a result on top of my head. Yeah, sorry about that. Yeah. But if your function is differentiable, right? So Lipschitz continuous essentially means that your gradient has bounded to null.
Yeah, the Hassen matrix large size.
Yeah. So that we actually used, right, in our proof, because we assume our gradient is bounded.
When
if you yeah, so we didn't go through the proof, but if you recall the theorem, we assume the gradient is bounded.
I see.
We assume the gradient is bounded. We assume the variance of the unbiased estimate of the gradient is also bounded. Right?
Okay.
And you actually can see that the variance actually appears inside the final expression. In other words, if you actually have large variance, the convergence actually becomes slower.
Good.
Right? So that's why we are doing this kind of derivation to reduce down the variance of the estimate, right? I mean, essentially, when we're trying to guess the gradient, we know that we have many expressions that gives us unbiased estimate, unbiased guess. I mean, you should definitely pick an expression that gives us the smallest variance, right? Conditioning on, they are all unbiased estimate.
Understood. Thank you.
All right, so that's the second part of today's lecture. So the last piece is, let's just put everything together and let's just revisit how we actually draw samples from this distribution, right? So that we can, form an unbiased estimate of the gradient now. All right, so we can just do this baseline version, right? So all we needed to do is just replace this expectation by samples. Okay? And we talked about how we draw SA from a state action distribution, right? So we can use the loading in and roll out process again here, right? So let's draw a SA pair from this distribution. And let's do a roll out to get a scalar y such that this is an unbiased estimate of my Q pi SA, right? So if you recall this picture, so this is exactly the loading in and roll out process to get this SAY triple. Right? So we randomly pick a time step with probability proportional to gamma to the power of h, and we're loading in, and we stop at this time step, and then we roll out. Right? Remember, this rolling in roll out process gives us this SA y triple such that SA is from d pi theta mu, and expectation of y is equals to Q pi theta SA. All right, so we can repeat again, similar to the supervised learning oracle that we were talking about, right? So we can repeat this rolling in, roll out process n times independently. And now we get a mini batch data set, right? That consists of state, action, and the scalar y. We have n such kind of triples. And all we need to do is just sum them together and take the average, right? And this is unbiased estimate right? I'm just replacing all the possible expectation by an empirical sample, right? I draw n such kind of samples, compute value for each sample, and take the average, right? And that should be unbiased estimate of the policy gradient. And in fact, if you set n to be infinite by this, central limit theorem or law of large number, this quantity should converge to the true gradient, right? All right, so now we can just put every piece together into this pseudocode framework, right? So this is super simple. Let's initialize theta 0. And again, there's a caveat. We don't want to initialize the theta such that the policy is deterministic. And if you're using neural network, we don't want to set this theta to be 0, right? Because backpropagation on a neural network with weights equal to 0 gives you gradient 0, right? So you're not going to make any improvement, right? So this is a different topic. This is the backpropagation algorithm, right? So you cannot start doing backpropagation on neural network with initialization equal to 0, right? So that does not work. Right? So now let's just repeat this policy, this gradient ascent algorithm, right? So let's just sample a mini batch data set based on the current policy, form this unbiased estimate, And then let's just do gradient ascent, stochastic gradient ascent. Right? So here I want to see expectation of GT is equal to
Professor, what happened to 1 by 1 minus gamma?
Shit. Okay, good question. Yeah, sorry about that. I will update the slides accordingly. So let's just multiply the Poisson factor. Yeah. Okay, cool. Thanks. Yeah, but even if in the implementation you forget about this 1 over 1 minus gamma, that's not a big deal. I mean, you get the correct gradient direction, right? So imagine you do gradient descent, you get the correct descent direction. It's just the scaling of the gradient, right? You might be able to just tune it on the step size, right? But you already find, the correct descent direction to go down, right? That's in some sense the most important thing.
Professor, I have a question.
Hmm?
So the gradient estimate you have right now, right? It's not the one with minusing the baseline, right?
Oh yeah. So this is the Q version. If you have a baseline at hand, just minus that, right? So what you will do is just do yi minus b si.
I'll
just replace that.
Thank you.
And in the homework question, you're actually going to try out a constant baseline, right? And that actually helps already. All right, so that's the algorithm basically, right? And one last thing that I want to mention is that in practice, to further reduce the variance, right, we might sacrifice the bias, the unbiasedness, right? So this comes to the thing that we talked about a lot in machine learning 101, which is bias and variance trade-off, right? So far, we have been talking about how to get unbiased estimate while trying to reduce down the variance as much as possible. But we really at a stage where we cannot really reduce down the variance anymore. So we have to now sacrifice the unbiasedness. So let's maybe aim for a policy gradient that is biased, but maybe the variance is even reduced, right? So the way you do it is that maybe we can use a supervised learning algorithm to estimate our Q function, right? So we talked about how to maybe estimate the Q function, right? Using a regression article. So we can do that. So we can sample state action pair from this distribution and we get a Y. So this is again the roll out process, right? So we can essentially fit a function F that approximates Q pi theta, right? And we can do this by regression article. And now we can approximate the gradient by just replacing the Q function by our estimate F hat. Okay, so this is approximating Q pi theta SA. So this is approximating V pi theta S. Right, so now this is probably no longer be unbiased because it relies on my estimator F hat, right? But the nice thing is that once we get this F hat, we don't need to rely on any roll out, right? Like we don't need to roll out at the current SA all the way to the end and sum of these rewards together, right? So that could be a very high variance process. So now we just replace a roll out by a simple function call, right? So F is a function now, right? Rather than a roll out. So we don't do a roll out anymore, right? In this expression. So that potentially could further reduce down the variance, but the cost is that now you actually give up unbiasedness. But which might be fine, think about when you do gradient descent, you don't really have to follow the exact gradient, right? As long as your gradient is within 90 degrees of the gradient, as long as your descent direction is within the 90 degrees of the gradient, you might be okay, right? Because you still sort of get some benefit of, descending, right? As long as, so let's say this is your gradient direction. as long as you follow this direction, which is less than 90 degrees, then you're okay, because this direction still has some component that is aligned with the true gradient, right? So that is the intuition why you could potentially sacrifice a little bit on the unbiasedness, right? But there's always this trade-off, right? So you have to sort of tune that trade-off in practice as well.
Professor, I have a question.
Yeah.
So you mentioned that we don't have to do row in, row out, right? But in order to look at F hat, you kind of have to do row in, row out.
Yeah, you have to do that. Yeah, but yeah. So you have to do that for estimating the F hat, but you don't have to do that anymore in the gradient estimation, right?
Ah, I see. Thank you.
All right, so there are many variants of the way like we do the gradient estimation using function approximation, right? So this approach, people often call it actor-critic. I don't know why this is called actor-critic. So actor means your policy pi theta, critic means your estimate F hat, right? So that's, people usually call it actor-critic. So in other words, you maintain two function approximation, right? One is for your policy, one is for your Q value estimate. So you keep updating them at the same time, every iteration. Right? So we're not going to go to the details of these methods, because with the fundamental stuff that we covered, you can actually do a lot of variants for this policy gradient formulation. Right? So this actor-critic is just one particular variant. All right, let's just summarize, what we covered for policy gradient. So we literally talked about 3 formulations. So they are all very common, the most fundamental 3 formulations, right? On top of which you can design, biased estimate by treating, bias and variance, right? So the first one is reinforce. So this is the simple importance weighting. And the second one is the policy gradient with the Q function, right? So this says that I should actually adjust my policy such that I give high probability to an action whose current Q value is big, right? So let's just aiming for some policy improvement, right? Let's just be slightly greedy with respect to the current policy, right? By just adjusting the policy parameter a little bit so that the policy actually picks an action with slightly more probability, right, for an action that has high Q value for now. And similar argument can be applied to the advantage function, right? We know that being greedy with respect to the advantage is always good if we know the advantage exactly, right? So here, let's just be incremental. In other words, let's just update the parameter of the policy a little bit so that next round, we will play the action that has high advantage with slightly higher probability. So that's all these, policy gradient formulations are doing, right? The first one, you should really think about them as the trajectory-wise, right? I want to push the likelihood of a trajectory onto those promising trajectories. In other words, the trajectory that has high total reward, right? That totally makes sense, from an optimization perspective, right? I really want to put high probability on the trajectory that has the highest reward, but I have to do it by respecting, the Markovian property, right? In other words, I can only control my policy, right? I cannot control the trajectory likelihood directly. And I control the policy so that I control the trajectory likelihood, right? It's just an indirect way to control the trajectory likelihood. Right, so the next lecture, we will talk about a trust region policy optimization approach. So this will lead us to this very nice algorithm called natural policy gradient. Right, so the next lecture might be a little bit confusing, but we will see, if you can get a good intuition of this natural policy gradient. So essentially, there's something called a natural gradient. Right, just for regular gradient, there's something called natural gradient, and you will actually see this formulation kind of looks like a Newton method, but we will explain the details for natural gradient next lecture. Right, and you will actually implement natural gradient in the homework, in the new homework. right? So that usually makes a huge difference on the performance of the policy gradient methods. Okay, so that's all I want to cover.